I'm Ira Goldstein, and I am the Director of Optimization and Exploration here at Altair. I would like to spend the next few minutes introducing you to the HyperWorks Design Explorer and Exploration inside of HyperWorks. Over the next few minutes, I'm going to give you a brief introduction to what the Design Explorer is, what explorations are, and then for the bulk of the time, I want to give you an example, a demonstration of the Design Explorer so you can see what it looks like, how it works, and how it can benefit you as a user. So first, what is the Design Explorer? The Design Explorer is an end-to-end workflow inside of HyperWorks, providing users with the ability to set up, execute, and interpret multi-run simulations, optimizations, or designs of experiment. And I'll talk a little bit about what those mean in just a moment. But why would we want to explore? What do we benefit? What do we gain from doing these explorations? First, you can gain a lot of insight into your product's performance. You can learn which attributes contribute most to a product's behavior. You can view trade-offs or predicted results for a product. You can review and plot and compare results for the various runs within the multi-run simulation, and you can even find optimal designs of your product. The Design Explorer also provides quick and easy evaluation setup. Everything is fully integrated and embedded within the HyperWorks application. What you'll see is that all of your setup and execution interpretation are done very graphically and intuitively, and there's a lot of tools to help you through this process. And finally, you gain solver independence. Often we want to do explorations or optimizations, and we're limited by a particular solver for doing so. But by using the Design Explorer workflow, we have a greater solver independence because the workflow works independently of your solver. So a quick word on explorations before we go into looking at the tools and a demonstration. The Design Explorer provides the ability to perform a couple different types of explorations, optimizations and designs of experiment. And often when people think about exploring or optimizing, they go right to optimization. And optimization is great. It provides an optimal answer to a specific question. So in other words, for example, what is the lightest design that I can achieve while ensuring that certain criteria are met? Like, for example, keeping stress less than a certain value or keeping a certain displacement within a range. And the Design Explorer certainly can help you set up optimizations and answer these kinds of questions. And this can be very, very useful. The benefit is we can arrive at these optimal answers, but it is dependent on the type of question that you ask. You know, what are your loads and inputs, and how have you framed the question to receive an optimal answer? Alongside of optimizations, we can also run designs of experiments. And this is where we systematically vary the input values of our simulation over a series of runs and evaluate the corresponding responses or output values to these changing inputs. And we can gain a lot of additional insights by running a design of experiments, and I'll show that in a demonstration. So let's take a look at what the Design Explorer looks like. And before I go into a demonstration, I want to give you just a high-level overview because I won't be able to touch on everything in the demonstration, but I want to kind of set the stage here. So what you're looking at is the latest HyperWorks interface, and across the top is what we call a ribbon, which is where we host various workflows inside of HyperWorks. And what you're looking at is the Design Explorer ribbon. And just very quickly, I want to show you how it's divided into different areas. First, we have an exploration tool, which is where you will create and manage all of your explorations. And you can have any number of explorations within a given HyperWorks session, so any number of DOEs and optimizations. The next set of tools are what we call inputs or design variables. And this is where you define the things within your model that can change over the course of a multi-run simulation. So things like part thicknesses, materials, material properties, and so on. Next, responses and goals. So these are the outputs. These are things that you might want to measure within your explorations. Things like mass or volume, displacement, stress or strain, forces, frequencies, and other things of measurables that you want to track throughout your exploration. And then you may have some goals on top of that. You may have an objective, for example, minimize mass, or some constraints like we just previously showed, keep your stress less than a certain amount or a displacement over a certain value. And then the final tool is the evaluate tool. And this is where this is just one button, but there's a lot of things embedded behind this tool. This is where you'll do your submission, and we can automatically submit and monitor all the jobs in your exploration as it's running, so you can see if it's going smoothly, or if there have been some issues, you can interrogate those. And then finally, in this same tool here, we have what's called the Results Explorer, and that's what's shown on the screen here. And I'll show this in an example, but this is where we provide all the tools for doing reporting and interpretation of your explorations. So let's dive in and look at a specific example. And this is just one example, but the tool is very agnostic to what type of model or example you're doing. It's domain. This is an automotive example, but the Design Explorer is domain agnostic. So automotive, aero, etc., architectural, and so on. In this example, I just want to give a brief description. It's an engine cradle model. This is an open source public automobile model. The blue part there is the engine cradle, and that's what we're going to be using for this example. In this example, we've applied some basic dynamic loading to the model, and we've observed a couple different modal frequency peaks, one for a torsion load at about 89 hertz, and similarly a bending mode at about 400 hertz. So we've set up a problem here where we'd like to explore this design a bit more and learn what parts are contributing to those different modes, how we may modify them, or how we may optimize this design under certain criteria. So we're going to set up a design space as shown here, where we have, in this case, 12 design variables. 10 are gauge or thickness variables for this part, and then we've defined a couple shape variables, one of which you see animating on the screen. And then we've identified 5 responses or outputs of interest: the mass of the cradle, and then the velocities and their corresponding modes. So now I want to jump in and demonstrate how I would set up a problem like the one that we just described, how you would use Design Explorer to quickly and easily set up the design space, evaluate the design of experiments or optimization, and then interpret and evaluate the results. So you can see here I've got the model open on the screen. I'm going to click on the Design Explorer menu option here and open the ribbon that you just saw previously. The first thing I'm going to do, and I'm just going to kind of step through left to right and walk through some of these different features and show you how they work, how you would interact with them, and hopefully how intuitive and natural they are to use for a HyperWorks user. So the first thing I'll do is I'll click on this little compass icon, and we're going to open the Design Explorer browser. And this is just where we can see kind of step by step what's going on, what's being created at any given time, what items or entities we're working on, and just kind of track what's going on through here. But we're not going to have to interact with this browser too directly. As I mentioned, mostly everything that we do, we're going to work right in the graphics area, in the context of the model itself, and that's what I feel makes this workflow very intuitive and natural, and that's true of HyperWorks in general now. So the first thing we'll do is we'll click on the plus icon here, and we'll create our exploration. And as I mentioned, you can create any number of explorations. We're going to just create one DOE to begin with. We're going to give it a name. We're going to name our study, and we'll just call it Demo Study. And we'll choose a folder location to store this information in. I'm just going to paste in a folder location that I previously copied for this demonstration. And we can rename our DOE, or we can accept the default DOE, DOE1. Okay, then we're going to go and we're going to create our design variables. So the first thing I'm going to do is just change my view here to isolate my design space. And I just had previously saved this view where I've got all the parts of interest in this assembly, which are the main parts of the engine cradle. I'm going to click on Gauge, which is where I'll define my thickness variables. I get a guide bar prompting me to select properties whose thicknesses or whose gauges I want to be used as design variables. And the easiest and simplest way to do it is I'm just going to drag a window across the screen here and select all 10 of the, you can see the number 10 here. I select all 10 of the components currently displayed. And then all I need to do now is just click Create, and it'll create the 10 design variables for me. Before I do that, I'll briefly describe what's going on here, because there's a number of different ways that we can define these variables. Whenever we define a design variable, it has a nominal or a baseline value, and that's simply being read off the baseline model as it exists here. Then I need to tell the Design Explorer how this value can vary over the course of an exploration. So in other words, a lower bound and an upper bound, or a minimum and maximum value for this variable. By default here, it's just going to create that as the lower bound and the upper bound as plus or minus 10% of the nominal value. And if I click create again, it'll just create all those for me. I can change these values to plus or minus 20% if I want. And then I also have a couple different ways of defining this variable, these variables. I can do it as a percentage like I'm going to do. I can set specific values for the lower and upper bounds just by keying in those values, or I can even set discrete values. If I know that, for example, each of these parts can only be made from a blank, for example, of fixed values, then I can enter those as discrete values as a table. In this case, I'm just going to change it to 20%, and I'm going to click create. And you can see with just a couple of clicks, I've got 10 design variables created now. In the example that I mentioned, we had a couple of shape variables. We had previously used the HyperMesh morphing tools to create shapes within the model. We can define those as design variables now as well. I can pick those graphically. They're not turned on at the moment. If I turn those on, we can pick them graphically just like the thicknesses, or I can click on this advanced selection dialog and I can choose the two shapes in the model and just click OK. And now you can see I've got two shape variables created. So that defines the 12 design variables that I had mentioned. We can click on any of these review dialogues and we can see a couple things. We have a summary panel where we can see our 1DOE and all the variables being used in it, or we can click on details and then see details of the design variables themselves. So I can see each of the variables, the thickness and shape variables at the bottom. We can see their nominal value, lower and upper bound, and we can modify these, as needed or as we like. There's also some preview tools here that I'm not going to show in the interest of time, but you can check on any of these. For example, the shape variable, and you can animate to see a preview of the shape, its lower and upper bounds. Okay, so the next step is we've defined all our design variables. Let's define our responses. I'm going to go ahead and turn back on the entire model so that I can make the selections that I need to make. And then our responses, you recall, are here in the next portion of the panel. And the responses that we're interested in are, in this case, a mass response. So we'll just click on the mass tool, and then I'll just click play or apply, and then you can see a mass response is created. And that's really all I have to do. After creating the mass response, I want to create my velocity responses as described in the slides. So I'll click on the displacement tool here, which has all of my nodal type responses. So I can click on that, and then in the guide bar, choose velocity. And again, the guide bar kind of prompts me for what it's asking me to do. So it's all should be very intuitive, and it's all, again, very graphics driven. So it's prompting me to select the nodes or nodes where I want to extract this velocity. And we're going to go ahead and select one node here, which is the point of interest. And now I get this micro dialog. Similar to creating the design variables, this is for capturing additional contextual information to the type of response, in this case, that I've defined or that I'm creating. And I can choose which load step I want to extract it from. There's some additional information if I pull down on the chevron here. But what I'm going to do just is open this post entity editor where I can see all the attributes of this given response. So I'm going to call this torsion velocity. And I'm going to leave it selected as velocity. I've already selected the node. I can select which load case or load step I want to extract this velocity from. In this case, the torsion load. Click OK. And now, because it recognizes that this is a dynamic or a frequency-based load case, it's prompting me with some additional information. So in this example, I'm interested in looking at the vertical magnitude of this velocity, and I'd like to look at the maximum velocity, so that peak that I showed in the slide, let's say between 10 and 100 hertz, for example. And then I can close that and select off there, and my torsion velocity response has been created. I can create a corresponding frequency response because I'm interested in tracking the mode associated with that velocity. So I click on frequency, and then I can click on play here, and then in its micro dialog, very similar, I can select which load step I want to use to track this mode. In this case, there's a normal mode step, and I'm interested in this case in tracking the seventh mode. So I've created this frequency. Maybe I would rename that as torsion. So I can continue on this process, defining additional responses. In this case, we had also a response, a velocity response, as well as a modal response for a bending mode as well. Those will be created in much the same way. Next, if I have any objectives or goals for my simulation or for my exploration, I can define those here. I'll just show quickly how to, this is a design of experiments, so it wouldn't necessarily have an objective, but I may choose to run an optimization later. So I can create an objective where I simply pick a response like the mass, and then I select the type of objective. In this case, I want to minimize the mass, so we'll leave that as it is. Constraints are defined in much the same way. So for example, I think our baseline torsion velocity was around 89 or 90 hertz. So let's say I want to take that torsion velocity and I want to constrain it to be no lower than its baseline value, which was 89 hertz, I believe. So now I've got an objective and one constraint. I can continue to build this up similarly for the bending mode as well. So once I have my in this case, exploration, in this case, my design of experiments defined, I would go and use the evaluation tool here to go ahead and evaluate this design of experiments. The evaluate dialog appears and it gives me some options in terms of the DOE type I want to run, the number of runs I want to use, if I want to run more than one job in parallel, and so on. The optimize button here is actually checked by default because I do have an objective. If I leave this checked, once I run my design of experiments, it will go ahead and try to optimize based on that DOE's response surface. I can turn that off if I just want to run a design of experiments. I can subsequently come back and run one or more optimizations on this DOE if I choose. And then we can go ahead and run, export and run the exploration. Again, in the interest of time, I'm not going to run it now, but I have right behind here another exploration of the same type that I had previously run. In fact, it's the same DOE. You can see the same 12 design variables. The responses that I just created, mass, torsion velocity, torsion mode, and then I had also created the bending, corresponding bending velocity and modes. In this case, we have an objective for the mass, ignore this velocity objective, and then a couple constraints similar to the one I just showed for the torsion velocity. And I evaluated this DOE. We can see on this run status dialog the runs that had previously been done for this DOE. So in this case, it was a 73 run design of experiments, and we can see all the runs completed successfully. So once that's done, I'm going to go ahead and open the Results Explorer. And as I mentioned previously, but didn't really show a lot of details, the Results Explorer contains, it's this browser here, it contains all of the tools and reports that can be used to interpret and post-process an exploration like this one. And let me just go through and describe the different tools that are available for interpreting the results of a design of experiments like this. So we have across the top here, there's 4 buttons: a run summary, the linear effects, trade-off, and scatter plot. And these are available for all designs of experiments. So let me go through and just kind of show how these might look, how these might work. We have a summary table, which is what's displayed here. And in this table, you can see one row for each run, this corresponding to the 73 runs, in this case in the DOE. And then each of the columns shows me the inputs or design variables, so all my thicknesses and shape variables, and then the corresponding response values for each of the runs: mass, the 2 velocities, and the modes that we were tracking. I can view all the results in a tabular form. We can also load results directly from here. So for any run of interest, maybe run 5, let's load results. And when I click load results, you can see that the results are loaded into a separate window here within HyperWorks, and now I have full control of the post-processing client. I can switch to that. Let's say mode 7 was my torsion mode of interest. We can switch to that mode. We can come down here, for example, and change. Maybe we want to look at the strain energies. Let's apply that. And then maybe we want to look at the animation of that mode for the fifth run. So we can do that. We can continue to build up a dashboard if we like. I can change the layout here to maybe a 2x2 window situation. Maybe in the lower right-hand one, I want to load results for, maybe I want to compare run 5 to my baseline run. So I can select the lower right window. Excuse me. And we can look at the 7th mode. We can animate these side by side to compare them and do an interrogation that way. Additional tools from this summary table, we can also load plots. If I change this client to a plotting client, maybe for those same runs, maybe for the baseline run, the nominal run, and run 5, I want to load and look at the velocity peak for this load case. So I can select load plots. I get the create curves window, and maybe I want to look at the vertical magnitude for the torsion load case and see where that peak is that I was interested in. So there's the nominal run. I can select load plots for run 5 and just overlay the peak onto the same plot there. So I can continue to build up this dashboard using the loading information from any of the runs. So for the DOE, I can overlay these runs. I do have an optimization here as well. It might be interesting to do the same kind of post-processing, comparing the nominal run to an optimal run, for example, instead of just 2 of these DOE runs. But the concept would be quite the same. Let's look at the next couple of tools, though. The linear effects here in the upper left corner. Let's switch to a response, maybe that same torsion response. And what this is giving us a look at is the linear effects or the sensitivities of each of the design variables to a particular response. So I've chosen that torsion velocity, and now I can see kind of a ranked listing of each of my design variables for this response. And what this is telling me, I can select these individually and see which one it's corresponding to in the model. And this is telling me that if, again, the sensitivity to this response, of this design variable on this response. So in other words, if I want to affect the torsion velocity, an increase in this given thickness here will have the greatest impact relative to the others beneath it. So it's giving me an indication, some insight into my design, and an indication if I want to affect a given response value, which design variables I should interrogate or investigate. And these are kind of in relative terms, so it's indicating that this thickness has a relatively greater impact, again, to the ones beneath it. It's also showing the correlation of the linear effect in colors, in 2 different colors. In this case, these are all negative correlations, meaning an increase to this thickness is expected to have a corresponding decrease in the velocity. If we look at the bending one, we can see that there's a bit of a mix here. So now we can see negative correlation highlighted in shades of blue, and positive correlation in shades of this pink or red color. So we can interrogate that way. The trade-off panel is interesting. For every design of experiments that we run, we automatically generate a response surface in the background, and then we can use this trade-off panel to, without having to run additional solver runs, we can move these design variable sliders, and as you see, the value of the design variable is changing corresponding to where I set the slider. And then down in the response table, we're getting changes to the predicted response. So in other words, if I want to see what would happen if I move all my design variables maybe to their maximum value or their minimum value, or set them to some discrete values, however I choose, then I can, without running a solver job, it's indicating to me that it predicts this velocity value peak would be at 7.6, and the corresponding frequency would be 86.6, and so on. And again, this is all predicted based on the response surface. If I want to verify this, I can do a verification run, which would run a single solver job with these values set as the sliders are currently set. And then I would be able to verify or validate that prediction. Finally, actually, let me come back here. Before I do that, let me switch to optimization just to show quickly. I ran an optimization as well, and the tools are similar, but I'll just highlight a couple differences. We get a summary table, which is now color-coded. So we can see in red any runs who violate a particular constraint, and the constraint is shown in bold. And it's indicated in red that run is in violation of a constraint. The black runs are feasible but non-optimal. Yellow runs have a nearly violated constraint. And then finally, the green run is the optimal run. So as I mentioned, you may want to load results and compare an optimal run with a baseline run. Or we have a new tool here called Compare Design Variables. And if I click on a given run and say compare with, in this case, let's compare with the optimal run with the nominal run, then I get a different contour up here in the left-hand window. Let me sort these. And this is showing me now the change in design variables between the two runs that I've selected. So in this case, between the nominal run and run 44, which is my optimal run. So it's a good indication of how the variables have changed. And we can see these have decreased by 18, 19, almost 20%. And some of these variables have increased in value. So it's an indication in my optimal run, as in this case, like where mass has been reduced, and in some places where the mass has been increased, but still arriving at the optimal run. So this can be a handy tool for comparison. Within the optimization results explorer, we have some additional plots here for plotting the iteration history. Let me just plot down here. For example, we can plot our objective, which was the mass, and see how it's changed over the course of the optimization and how it's been reduced from its baseline value here. It did go up while the optimizer was searching, but ultimately has been reduced as per our goal. So that's some of the additional tools that are available. So I think that's what I wanted to show for a quick demonstration. Let me come back here and just wrap up. So in quick summary, we had a look at the Design Explorer. The Design Exploration, I feel, is an underutilized but very powerful set of tools for CAE users. As we've noted, you can gain a lot of insights into your design by performing these designs of experiments or optimizations. And these tools are often not available. We've tried very hard to integrate Design Explorer directly within the HyperWorks environment. So it's available to any user of HyperWorks just right out of the box. It provides a beginning to end workflow. I hope that you've seen that it's easy to use, intuitive, and it is accessible. Again, you can gain a lot of insight by using it. So I would encourage everyone to take a look. If you have additional questions or need some help, please contact your local account or support person, and we'd be happy to provide additional information and try and help in any way that we can. Thank you very much.